Hi everyone. Today I'm going to present our work aligning neuronal coding of dynamic visual scenes with foundation vision models. As we all know, our brains represent the ever-changing environment with neurons in a highly dynamic fashion. The temporal features of visual pixels in dynamic natural scenes are entrapped in the neuronal responses of the retina. It is crucial to establish the intrinsic temporal relationship between visual pixels and neuronal responses. Recent foundation vision models have paved an advanced way of understanding image pixels. However, neuronal coding in the brain largely lacks a deep understanding of its alignment with pixels. Most previous studies employ static images or artificial videos derived from static images for emulating more real and complicated stimuli. Despite these simple scenarios effectively help to separate key factors influencing visual coding, complex temporal relationships receive no consideration. In this work, the natural scene stimuli are used, which consist of two video clips with rich natural scenes, named Movie 1 and Movie 2. This work focuses on studying the retina encoding mechanism by recording RGC spikes in response to visual stimuli. These two videos show different levels of scene complexity in both spatial and temporal domains, which presents a challenge for the building and testing of encoding models. About the neural responses, a total of 90 well-responding RGCs were used for training and testing. To align frame rates, neuronal spikes were grouped into spike counts at intervals of 33 milliseconds, resulting in a dataset with 30 Hz response for each trial, in line with the sampling rate of 30 Hz used by video stimuli. To decompose the temporal features of visual coding in natural scenes, we propose VEST. It is a spatio-temporal convolutional neural network and fed with a self-supervised vision transformer prior. The model demonstrates robust predictive performance in generalization tests, and in the ablation study, we demonstrate the significance of each module. Meanwhile, we introduce a visual coding evaluation metric designed to integrate temporal considerations and compare the impact of different numbers of neuronal populations on complementary coding. We divide the model into two parts: the video features extractor and the spikes alignment module. In the video features extractor, we utilize the Dino V2 to be a prior for spatial information of image pixels, and utilize the causal 3D temporal convolutional module to extract the spatio-temporal features of visual pixels at different scales. Then we feed the extracted features into the spikes alignment module with biological receptive fields. The spikes alignment module is designed to align visual pixels feature space with the neuronal responses space, which implemented by 4 causal multiscale spatio-temporal module, named CMSD. It is worth mentioning that in the CMSD module, we manually identify spike durations to be the kernel size of modules. We calculated the density function of entire neural responses duration, and identified several high-frequency durations, which we use as feature-sensitive spans. Durations refer to the durations of firing rates ranging from 0 to maximum, and then back to 0. We estimated their distribution using kernel density estimation, then selected some from them. About the loss function, we initially used the root mean squared error loss to train the model. However, the RNSE loss is very sensitive to the time shift and modulation of the sequence. To address the issue, we introduced the soft dynamic time warping loss, which is a differentiable version of dynamic time warping and is a non-Euclidean distance metric as well. Meanwhile, to reduce the model's predictions of meaningless negative responses, we add a negative ReLU function as a penalty term to the loss function. In the task of neural encoding, the Pearson correlation coefficient is commonly used to assess the reliability of predicting neural signals. While CC considers the macro trends of the entire sequence, it lacks the detailed consideration of temporal information or dynamics over time. In line with the departure point of the VEST loss, we attempt to introduce the factor of spike duration to observe the neuronal encoding performance of the model, which fully considers the characteristics of the neural response. In the experiments, we test the model on 2 tasks, within movie and across movie prediction. In the within movie task, training and testing data are taken from the same video, where pixel context is conserved. In the across movie task, training and testing data are taken from the different video. However, our focus places a significant emphasis on spatiotemporal modeling tailored for neural encoding tasks across different videos. Using the same videos shows relatively good CC. However, a significant improvement in across movie prediction between videos can only be observed with VEST, and other models lack the generalization ability. Furthermore, to investigate the contribution of each model module to prediction performance, we progressively removed or replaced different modules and observe changes in CC. We found that the spikes alignment module played a more significant role compared to the video extractor, and the VEST loss had a non-negligible impact on achieving more generalized neural encoding as well. Additionally, in conjunction with Figure B, we observed that removing the Dino V2 prior had a significant impact on the model, and excessively deep Dino V2 features did not bring about more gains. Therefore, selecting an appropriate spatial feature prior for RGC visual encoding tasks requires careful consideration. Meanwhile, we compared the model performance with RMSE loss and VEST loss. In all experiments, we observed that the VEST loss outperforms RMSE. This indicates that considering temporal variations in the loss function is crucial for neural encoding tasks. The prediction results for neural encoding tasks often do not involve a fixed number of neurons. Therefore, we ask, is it optimal to construct an end-to-end model capable of simultaneously predicting all neural responses? Ding explored the benefits of complementary encoding for neural encoding by constructing a high-dimensional representation manifold of responses of the RGC population. We designed an experiment to observe the impact of different numbers of neurons on the model's performance. And we found that similar to biological RGC responses, a redundant encoding space allows VEST to better match real response outcomes. Thank you for your attention. If you have any questions, please feel free to contact us.